All right, let's tackle one of those questions that can really make a difference on a GCSE paper. We're looking at a chunky 5-mark coordinate geometry problem. Now, it might look a little intimidating at first, but trust me, the solution is actually pretty neat. We're going to break it down step by step, and we'll use the official mark scheme to see exactly how you bag every single one of those marks. Okay, so here's the question. We've got 3 points, P, Q, and R. Now, you can see P and Q have fixed coordinates, but R has this unknown variable k in both its x and y coordinates. And our job is to figure out the possible values for k that make the whole setup work.
And this is the golden ticket. The fact that the angle at R is a right angle. That is the clue that unlocks this entire problem. It tells us that the line from P to R is perpendicular to the line from R to Q. So, when you see right angle in coordinate geometry, what pops into your head? For me, there are 2 big methods we can use.
So, let's dive into method 1. The gradient approach. See, if we know 2 lines are perpendicular, that tells us something really specific and useful about their gradients.
And here is the rule you absolutely have to remember. When 2 lines are at right angles to each other, you multiply their gradients together, and the answer is always, -1. That single fact is going to power this whole first method.
And check this out, the mark scheme tells us that just starting this process, just trying to find an expression for the gradients of PR or QR gets you your first mark. So, let's go get it.
First up, let's find the gradient of the line PR. You know the drill, it's the change in y divided by the change in x. We just plug in the coordinates we have for P and R, do a little bit of tidying up, and we end up with this expression right here.
And now we just rinse and repeat for the line segment QR. It's the exact same formula, just with the coordinates of Q and R this time. And that gives us our second gradient expression. Simple as that.
Okay, so we've got our 2 gradient expressions. The mark scheme is super clear. The next mark is for putting these 2 pieces together using that rule for perpendicular lines we talked about. So we take our first gradient, multiply it by our second gradient, and set the whole thing equal to -1. And just like that, we've built the main equation for this method. Now you just have to solve this for k. But hang on, what if you didn't even think about using gradients?
Well, there is another way in, and this just shows you how flexible math can be. Think about it. If the lines PR and QR meet at a right angle, that means the points P, Q, and R have to form a right-angled triangle, right? And what do we know about right-angled triangles? Well, good old Pythagoras' theorem, of course. Since the right angle is at R, the side opposite it, that's PQ, must be the hypotenuse. So we know that PR squared plus QR squared has to equal PQ squared.
And you know what's really cool? The mark scheme explicitly says this is a totally valid alternative for your first mark. It shows there's more than one way to get to the answer. So let's work out the squares of these lengths. First up, PR squared. To find the length of a line, we can use the distance formula, which is basically just Pythagoras again. It's the change in x squared plus the change in y squared. You plug in the coordinates and you get this expression.
Next, we do the exact same thing for QR squared. Plug in the coordinates for Q and R, run through the calculation, and boom, we get the expression you see on the screen. And finally, the hypotenuse, PQ squared. Now this is the nice part. Because we have the actual numbers for P and Q's coordinates, this calculation doesn't even involve k. It just spits out a clean number for us to work with, 221.
Now, here's where it all comes together. It doesn't matter which path you took, whether you went with gradients or you chose Pythagoras. After you expand all the brackets and simplify all the algebra, both methods lead you to the exact same place.
How neat is that? 2 completely different starting points, and they both converge on this single quadratic equation. That's when you know you're on the right track. Okay, so now for the final part of the puzzle, we just have to solve this thing. So let's quickly factorize this quadratic. This is a classic skill you need to nail to get those final marks. We're on the hunt for 2 numbers that multiply to make -84 and add up to +5. A little bit of thought, and you'll find they are +12 and -7. So we split that middle term, factor by grouping, and we land on our 2 neat little brackets, 2k minus 7 and k plus 6. So if these 2 brackets multiply together to equal 0, that means one of them has to be 0, right? That's the key. So we just solve each one. If the first bracket is 0, k is 3.5. If the second bracket is 0, k is -6. And those are our 2 possible solutions.
Okay, so we've got our 2 answers, but did we nail it? Let's check in with the official mark scheme one last time to see if we've earned ourselves the full 5 marks.
And there it is. The mark scheme confirms it. Our 2 answers, k equals -6 and k equals 3.5, are both spot on. That's a perfect solution and 5 marks in the bag.
And that's a wrap on that question. You know, it's a great example of how one little clue, that right angle, can open up different ways to solve the same problem. It really makes you think, though. Which method felt better for you? The gradient approach or good old Pythagoras? It's always interesting to see which one people prefer.